introduction, okay? Okay, let's start. Hello, everyone. It's my great pleasure to introduce our today's first speaker, Audrey Nsamela. She comes from Dresden University of Technology, and her talk's title is Microfluidics for Microswimmers, Engineering Novel Swimmers, and Construction Swimming Lanes on the micro scale, a tutorial review. So let's welcome Audrey to share her research. Please go ahead, Audrey.
Thank you. Thank you very much for this introduction. I'm very happy to be here to talk to you a bit about my project and also the topic of the review that we published earlier this year. So yeah, the topic will be around microfluidic for microswimmers. First of all, I just wanted to give you a brief introduction about myself, just to give you a bit my background. So I'm from Belgium, and there I studied my bachelor in engineering and my master in physics engineering at École Polytechnique de Louvain. So the master was part of a double degree. I did the second part for 2 years in Canada, where I did a master in biomedical engineering in Polytechnique Montréal. And I had the opportunity to work on a research project on the fractionalization of gold nanoparticles with antibodies for cancer cells targeting, but I won't go into details of that. And I'm currently in Paris for my PhD. I will explain you a bit the context of that in a moment. And yeah, in my free time, I'm a nature and dog lover. So yeah, this is the big picture. So the context of my PhD project is a little bit special because it's part of an international training network, an ITN called Active Matter. So it's basically 15 different PhDs, different projects in all around the world, especially in Europe, that are working in different topics related to active matter. This is funded, we're all funded by the Marie Curie grant, and it's part of a European program called H2020. And these are all the beneficiaries of this grant and of this network that are collaborating and or hosting PhD students. So the aim of this consortium, so this group this network, is to collaborate, promote collaboration between the different parties, and also to disseminate information. So we we only publish through open access publishing, and we also do some outreach activities to give, let's say, a view of active matter and what can be done in this field to a wider audience. And the last goal is to innovate and bring let's say, bring the research closer to a market, to a product, and to real life applications. And this is especially important and an important part of my project because it's part of one of the 3 projects that is done in companies. So we have 2 companies. You have Elvesys here and Cherry Biotech, and my project is done at Elvesys. So the brand is Elveflow, and in collaboration with TU Dresden, with Juliane Simmchen. So typically, how does that work, a PhD in industry? Because that's a little bit different than a PhD in academia, but basically you start with a PhD candidate. In this case, that is me. I'm doing most of my research and my experiments at the site of the company. So we have some labs there in Paris, and I have an academic supervisor, I have an industrial manager, and basically my task is, common to all the PhD students. I'm doing research. I have questions that I'm trying to answer. I will tell you a bit about that topic in a moment, writing a thesis and so on. And then I have other tasks that are more, let's say, industry oriented. For example, this is the writing and publishing application notes on the website of the company. So these application notes are basically experimental methods that I'm using my research to make a proof of concept with a microfluidic setup. And then I publish these results in a very, let's say, simple way, and just to tell the users, okay, I use these instruments to produce that kind of results. So if you want to do something similar, you can do this with also in a similar fashion. And another part of the work is to publish reviews on the website. These are not peer-reviewed reviews, but it's also kind of, I mean, it's the same principle. It's just that these are more the activities that are that concerns my PhD project. So the topic in particular, that is, so I'm part of the Active Matter Consortium. So there is some active matter in the topic. And the aim is to develop a microfluidic platform to study and engineer artificial and biological microswimmers. So typically, this is just an example of a microfluidic setup to illustrate how the different components. So you have a microfluidic, you have a pressure pump, which is controls the flow of your fluid from the samples. Into the microfluidic chips, where I will perform and you perform the experiments, and you can control all of this via software and automate the processes. And there I'm studying, I'm using sperm cells as a model for biological active matter, and I also did some experiments with artificial microparticles, active particles. And another side topic that I've been working on is to use a microfluidic to generate polymeric and lipid nanoparticles for drug and vaccine delivery. So this is basically the same principle. It's just a little bit aside from active matter, so I won't go too much into the details of that. So then I wanted to give you I'm not here to do an advertisement, but just to give you an idea of what Elvesys is doing, why also are they interested in collaborating so much with academia and research, and why active matter. So I don't know if you're not, or you might be acquainted with those instruments, but they are developing microfluidic instruments for researchers. To really pursue their research and go further in the state of the art of their field. So they have many different products, but yeah, basically the OB1 is the flow control. It's a pressure pump. So if I've been working with microfluidics, you know that you need a pump to push your fluid and to drive your fluid into the system. So this can be one type of pump, and you have other types of components. I won't go into too much details. And typically so there are many things that can be done with microfluidics, many types of applications. I won't say them all, but it goes from lab on chip to organ on chip, droplets. It's especially important for biomedical applications, so diagnosis, drug screening, and so on, but also for flow chemistry, chemical synthesis, microreactors. And this is why, I mean, you might ask yourself right now at this point, how can it benefit the field of active matter? So this is actually what we tried to let's say to review and to give to our readers in this review, Microfluidics for Microswimmers. So microfluidics can benefit the field of active matter and microswimmers in many different ways. We really isolated 3 of them that have been, flourishing in the recent past, and we try to give an update on all these different works. So it can be used for the fabrication of these microswimmers, and I will present a few different techniques on that. To the actual applications and testing the applications of those microswimmers, because right now we know that the world of microswimmers and micromotors is quite new, and they're often not already applied to large scales and real life applications. But microfluidics provide a really good way to cross that bridge, let's say, and bring this a step closer to applications. And this goes with the design of environments and control environments with confinements, flow, gradients that could better mimic the environment in real life. So, for example, for biological application, and microfluidic is a very useful tool for that too. So I will describe a little bit more what has been done in a non-exhaustive way in these three key points. So in the fabrication of artificial microswimmers, so droplet microfluidics has been used by many groups actually to fabricate mostly soft, let's say, soft matter microswimmers. And in this case, they used a flow focusing device to generate droplets and to fabricate those marangoni swimmers. So those marangoni swimmers are basically active and moving self-propelling droplets. They use a gradient of surface tension to propel themselves. And droplet microfluidics, this is also another example of how droplet microfluidics has been combined with another technique that's called stop flow lithography to create bubble propelled hydrogels with integrated nanoparticles. So this is a way with microfluidics to easily integrate. Here they integrated two different cores containing different types of nanoparticles. So you have the platinum particles that are responsible for this chemical reaction and for the propulsion of these microswimmers, and you have the magnetic nanoparticles for the guidance of these swimmer. This is a very interesting also way to fabricate them, and also you can imagine how, I mean, in microfluidics, you can really produce highly monodisperse droplets. And since the shape and the size of these swimmers is important on their swimming mechanism, it's really important to have a high monodispersity of their size. Another example of this stop flow lithography technique is here used to fabricate helical microswimmers. So these are helical fibers that is used by a technique by this called pinning and spiraling, and then by applying UV. So this is basically a gel that is spiraling inside another matrix, and by applying a UV through a mask, you can selectively polymerize parts of these this long helical fiber. And then by dissolving the part that have not been polymerized, you have very defined sections of these helical swimmers. And here in this case, they integrated magnetic nanoparticles to guide them and to have this self-propelling motion of fibers. And this is also a very interesting tool to try to replicate flagella, because this is also a very tricky thing to do in microfabrication. You can also, so there is not only artificial microswimmers that can be fabricated. You can also fabricate biohybrid or bio-inspired microswimmers. And in this case, for example, this group has used microfluidic traps to trap microcubes as a first step, and then attach flowing bacteria on these cubes, and then by reversing the flow, they managed to release those bacteria-driven cubes. And this is a very, I mean, this was one of the first group to perform this, the fabrication of these biohybrid microswimmers in such a way, and these microfluidic traps are very, let's say, straightforward to do with lithography techniques. And then this other group, this other group used the same helical, let's say, fibers that I already presented earlier, and they actually show the potential application of these fibers fabricated through microfluidics. So here in this case, they used it as a template for cells, and that could potentially be guided and used in biomedical applications, for example, for cellular, muscular reparation, and other types of applications. But in this case, there is an issue that has to keep in mind, is that these bio-inspired and biohybrid like microswimmers have a limited cycle of life due to the fact that they have biological components that are not immortal, let's say. So the second part that is very important in this matter is how microfluidic can be used to design environments, and that is so confinement, flow, and gradients. And mostly what we found is that the fabrication and the control of gradients is also a very important issue, and a very important topic that can be achieved with microfluidics. So in this case, they used this group of Baraban used microfluidics to perform a flow-based gradient of hydrogen peroxide, and they actually showed this chemotactic behavior of tenous particles that were able to cross the stream and go into the higher concentration area of hydrogen peroxide. Another group used a microfluidic maze to assess the chemotactic behavior of marangoni swimmers. Other were fabricating biohybrid neutrophils and also using a microfluidic setup to perform a gradient and a chemotaxis assay. And also for you can also, there is concentration gradients that you can perform, but you can also perform pH gradients in the same type of designs. And this is super useful to assess the pH taxis of biological matter. And here they compared the pH taxis of bacteria bots and found it was similar to swarms of regular bacteria. So all this work could not be done without microfluidics, because this is especially useful for really controlling the environment and the gradient. And it could be not done in bulk. But then the other, the end goal of this is also to bring closer the microswimmer research to applications. And mainly this is done, we found a few different applications where that was very important. So the pickup and transport of loads, and in this case, this group used helical microswimmers, artificial ones, to capture immotile sperm cells and to perform artificial fertilization. And this is really this could be a game changer into solving male infertility, for example. This was an early work, but it was it's very promising for the future. This is another example of a pickup and release of a load by a nanomotor. In this case, artificial nanomotor based on carbon nanotubes. And they did this experiment in complex microfluidic channels, and you can see really the pickup of this load, release, and then the nanomotor then swimming away freely. So this could all be, bringing a step closer to, drug delivery applications or other types of fields. Another really interesting application is to use microfluidic to create concentration devices. And here they model these microfluidic traps to concentrate rods, self-propelling rods, which could be bacteria, which could be also artificial swimmers. And for this, you can think of many applications where, for example, you need to have a high concentration for sensitivity issues, to solve sensitivity issues, or you can imagine this is a way to observe in a really local way collective behavior of microswimmers. So these are all options. And so there are obviously challenges that are related to the let's say the intertwined relation of microfluidics and microswimmers, because this is quite new and there are still many ways to explore it. But one of the challenges is the scale up. First, the scale up of the fabrication of the devices of the microfluidic device, and then also going, let's say, in real life applications, you might have larger volumes. So how can you transfer from the micro scale and micro volumes to a bigger scale? Is this if this is transferable? This is one of the problem, and also for biomedical applications, the biocompatibility and the functionality of these microswimmers is very critical. And this needs to be really accounted for when thinking about really getting to real applications. And the other main or big challenge is environmental issues, because there are certain, there are applications in environmental remediation, for example, but we need to think about let's say the recycling, or the way we deal with single use, let's say microfluidics, or find maybe new materials. These are all like challenges that that needs to be addressed if you want to be more environmentally friendly in the future. So to finish, I wanted to give a little bit of side information on this topic that is very present in our group in Dresden, in the Simmchen group, because they also have been doing work on microfluidics and microswimmers. And this was one study where they used capillary microfluidics to observe the cross-stream migration of platinum silica genus particles. And they used a pressure pump to induce a flow in this capillary and to try different conditions with either passive particles or no flow. And they really could observe a clear cross-migration behavior of these particles. Another paper, another work that was done by a member of the group, and using microfluidics. So they use these traps, microfluidic traps that is shown here in the picture, to create those oil and water interface. And in the same, this is really the advantage of this method, is that in the same field of view, you can have at the same time, you can have these oil patches, so these liquid interface between the oil and the aqueous phase containing hydrogen peroxide, but you also have solid liquid interface. So you have both in the same conditions, in the same setup, you can both have your control and your test experiment and compare it directly. And what they found is that although there was a pinning of the particles at the interface, there was a similar motion pattern. Whether the particles were located at the liquid-liquid interface or on the glass substrate interface. This is another work that has been published quite recently by also Priyanka. So I explained to you the stop flow lithography technique to fabricate microswimmers, and this is exactly the topic of this work. So they used stop flow lithography to fabricate letter-shaped microswimmers. These are hydrogels that contain an active part at their extremities, and that this active part is basically an enzyme that degrades the hydrogen peroxide. And then you can have, by varying the shape of the mask, you can have different shape of swimmers and really engineer and have different motion patterns. And here you can see the different motion patterns of these swimmers depending on their shape, because we know that geometry is a very important factor in the motion mechanism of microswimmers. So this could be really I think there is a lot more to explore on this, and I think yeah, this is a very interesting topic. So this is it for my part. I really would like to thank you for listening. The take-home message is that I just give you a description of my PhD project that is done in industry and this ITN active matter context, and also through the description of our review and the work that has been done in our group, how microfluidics can be used in the research on microswimmers. So it is really a powerful tool for new fabrication technique. It can be used to better mimic real-life conditions by applying flow, gradients, and confinements, but also controlling all these parameters very precisely. And I think, yeah, there is so much more to explore on that topic. So yeah, thank you very much for your attention. And if you have questions, please state.
Thank you, Audrey. Thank you for a wonderful talk. Now we are going to the Q&A section. If there is any question from the audience, please feel free to ask question.
I think there is a question in the chat.
Oh, okay, there is a question in the chat.
Will one see directed motion of tracer particles if they are added to the Marangoni flow-based microswimmers? Directed motion of tracer particles. I'm not, you mean, I'm not entirely sure to understand the question. You mean if you introduce, I don't know who asked the question, but I mean, I would say yes, but I'm not sure if the person who asked this, does it result in bulk flow? Oh, okay, I think I understand. Okay, so I'm not an expert on Marangoni microswimmers, but I think that the flow that results is more local, but also it depends obviously on the concentration of these, let's say, these droplets, active droplets in your solution. But yeah, I think there is obviously local flows around the swimmers. I'm not entirely sure if this induces bulk flow, but that's a very interesting topic, I think, to investigate. There is another question. How does the letter-shaped hydrogel fabricated in details? Page 17. Can we use this as technology to fabricate other patterns? Okay, I think so. This was here. How does it? So technically, this is fabricated by stop flow lithography. So you have here I will move maybe this. You have this microfluidic chip with here 3 inlets. So this is the fabrication method for the Y-shaped microswimmer. So by really, I mean, you can think of different designs for this chip depending on how you want to, I mean, what part you want to be active, what shape you want to define. But basically, the shape is determined by the mask that you apply, photo mask before the objective. So yes, totally, you can fabricate other patterns. I would advise you, if you're interested in that topic, to contact Priyanka, who has been done great work on that subject, or contact me later. But yeah, definitely you can fabricate other patterns. Okay, I have another question. Did Everflow evaluate the market they expect to gain from active matter research? That is a very good question. I don't think so. I don't think so that they evaluate. So typically, what they, I mean, I think so. The way that they how to say, you know, you have the end goal of what the researcher are working on. So they have their research, they have the subject that they want to look at. But in order to do that, you have all these, I mean, to make the setup, to fabricate, to have the components, to control the flow. This is all part of what's really, you know, useful for the company to promote. But I don't think they evaluate this, especially for active matter research. But I know that some part of, I mean, of the project and some part of the setups are connected also to other, you know, fields or other. I mean, they want to reach a wide audience, obviously. So they really try to see, okay, this is very useful for them in this field, and this is also very useful for this other field. So we're gonna, you know, we're gonna tackle this issue and try to make a setup for this. Yeah. Hope I answered your question.
Thank you. Thank you for your answer. So any more questions?
Looking to the future, what markets do the market wants to focus on in active matter? I would say that is, I think this is quite early to say. I mean, I'm not. So right now, I think this is a tricky question, because right now the active matter research I think, let's say, it's quite early. I think in the stage of bringing something to a market. So, and it's more, you know, it's also not very known actually to let's say, I think it's quite a new field. So I don't have a clear answer on that question. I wouldn't. I don't know.
I guess what I was trying to ask is, since you work in industry to some extent, is, you know, there are many different aspects of active matter that is interesting and potentially useful, but industry has to make a bet on certain applications, and I was just wondering, where are they betting?
Okay, so I think what I imagine, and from what I know that the subject they're working on, there are two topics that also I was presenting earlier. So the fabrication, of swimmers, well, by stop flow lithography or droplet microfluidics. This is a big, I think, very important part, and microfluidics can answer a lot of issues in that sense. But and another part is to, let's say, I think probably the gradient, the establishing of gradient and the study of active matter in gradients, because this is not only useful to active matter, but to, you know, a lot of, I mean, it's very interdisciplinary, I think, topic. So this is quite, I would say, would be a safe bet. But yeah, to answer also the previous question, they didn't really do like a market research on that specific topic, because this is, I mean, they also are working on many different applications. So I would be curious to know the the outcome of this, but I really can't really tell for sure.
Any question? If no more question, we will thank Audrey again for his wonderful talk and her answer. Sorry. Thank you, Audrey.
Thank you.
Hello, Jeffrey McNeil.
Yeah, hi.
Please share your screen. Thank you. Okay, I can see.
Everybody see that?
Yes.
Very nice. Okay.
Also, I will give you an introduction before you start. Okay.
Yeah.
Thank you. Okay, let's start. Our second speaker today is Jeffrey McNeil. He's come from University of Pennsylvania, and his talk title is Purely Viscous Acoustic Propulsion of Bimetallic Rods. So let's welcome Jeffrey to share his research.
Yeah, thank you so much. Yeah, like you said, my name is Jeff. I'm a fourth-year PhD student at the University of Pennsylvania with Professor Tom Malou. You know, I like Philadelphia a lot. I like to include pictures in my slides. So, you know, here's Philadelphia throughout the seasons. And like you said, I'm going to be talking today about acoustic propulsion of nanorods. But more generally, I also want to kind of describe acoustics in general. It's a complex and relatively new part of microswimmers and active matter. And I think it's really important to kind of outline the theory and a little bit more about how you use them in general, more than just focusing on this one topic. So of course, you know, when we want to get motivated, we have to think about why we want to study acoustic propulsion in general. We already have so many great ways of propelling different types of swimmers via chemical power, magnetic power, things like that. And definitely one of the biggest prospects is in biomedicine, because acoustics are already very mature and clinically relevant. You know, there's already been multiple demonstrations of acoustically powered motors for biomedical applications, but also you can get incredible images like this one from various types of ultrasound diagnostics and things like that. And so if you can come up with good biomedical applications, the translation seems obvious. But even more than that, especially what my boss Tom likes to focus on are kind of the fundamental applications or the fundamental science and what we can learn from these things. So first of all, you know, I'll talk about, you know, bimetallic nanorods swim at acoustic fields. And for a while, this really stumped us, but it allowed us to learn a lot about ultrasound matter interactions and how these things work. And beyond that too, it's another interesting way that we can maybe create self-organized systems that have interesting properties. You know, again, we already have seen this with magnetics and chemical power. So how can we apply this as well to acoustics? And again, just to start off, I want to kind of dive into the theory so that people understand a little bit more what we're doing here. And basically, the way to think about an acoustic wave, sound wave in general, is like a pressure wave. So much like a light wave is an electromagnetic wave with crests of let's say electric and magnetic fields pointed in opposite directions. An acoustic field is kind of a pressure wave. So you can imagine some ambient pressure that you're sitting at. And when you apply an acoustic wave, you see an increase and decrease in pressure at the respective crests of this wave. And one of the examples I really like to include are, for example, bubbles. How might this have an effect on the environment? And the way you can think about this is if you have a bubble sitting in a solution or anything like that, at ambient pressure, it's going to be some static size. But at the peaks, at the positive peaks of these waves, you're going to get an increase in pressure that decreases the volume of the bubble, like by applying pressure. And at the negative crests, you're going to actually get an increase in volume because the bubble's now feeling a negative pressure. And in general, we do these types of experiments in acoustic cavities. So for example, if we usually use silicon wafers with a piezoelectric chip epoxied to the bottom. The piezoelectric is made of something like lead zirconate titanate that actually changes its volume in the direction of these electrodes when you apply a potential. So basically by applying a sine wave potential of the same frequency, we're able to achieve sound waves of some desired frequency. And then a lot of the experiments I'll be showing today are done at acoustic standing waves, which means that if you make a cavity with a piezoelectric and some sort of reflector, usually just a regular glass slide, and you meet the half wave condition of this cavity of height h. By applying an acoustic wave at half the wavelength of the cavity height, you're able to establish an acoustic standing wave. And typically things that are perfectly symmetric will just go to the area of lowest pressure and levitate at the point between the glass slide and the silicon wafer. But where things started to get really interesting, and basically where this kind of area of research was born, of course, Tony Wong has been doing a lot of microfluidic based acoustic experiments for a while, but nobody really made a microswimmer before 2013, where we kind of discovered that these bimetallic rods swim at acoustic pressure nodes. And again, this really stumped us and we had no idea what was going on and we really wanted to explore it further. So just in general, before I start getting really into the microrod stuff, I wanted to talk about acoustic propulsion in general. Based on what I just told you, there's two types of acoustic propulsion that are really possible. The first one is with traveling waves, which means you kind of ignore what I told you most recently with the standing waves. And these are microswimmers that can be powered just by applying a traveling acoustic field. So like one example are these asymmetric bubble swimmers, where you have this asymmetric cavity in which you've trapped a bubble, and this generates acoustic streaming or fluid flow out of the open end of the bubble. And then there's also been one single example of a swimmer with a flexible tail, where the theory is that the oscillations from the acoustic waves vibrate the rod and kind of cause this sperming type motion. And then, of course, you can have acoustic standing waves where with free bodies, basically you start vibrating things that have high density. And so if you have some free body at an acoustic standing wave, it's going to oscillate up and down. And these oscillations are going to drive fluid flow that can be used to drive propulsion. There's also a lot of work with surface structures that can generate fluid flow. And again, this is kind of vibration of these structures at ultra high speeds that's able to drive fluid flow around sharp edges, for example. And then what I'll really talk about today are these asymmetric bimetallic rods that we have a nice working theory, I think, for why they are actually Purcell motors, kind of like sperm. And if you had to break them down, I would say that that traveling wave propelled swimmers are much more relevant for biomedical applications and things like that, because really you'll never establish an acoustic standing wave inside somebody's body. We need to get away from that idea if we're talking about biomedical applications. Really, bubble swimmers in that respect, I think, are the best things to think about. They will work at really, really low acoustic powers, and so that makes them very biomedically relevant. But it doesn't mean that acoustic standing wave propulsion is any less valuable. We can learn a lot about physics and microfluidics and all sorts of different things by studying interactions at these setups. So again, just to talk a little bit more broadly, I'll talk a little bit about our work on bubble propelled motors. These have actually been created before. We're not the first people to do it, but we were really excited to see these really novel properties from a very simplistic design. And the way that we make these is through nanoscribing. So a nanoscribe is a 2-photon polymerization laser system that's able to 3D print at the micro and nano scale. So what we're able to do is define the shape of this cavity with some SU8 type polymer. We add a layer of nickel to make this thing magnetic. In real applications, when we started this, we skipped this gold layer, but then actually the buoyancy of the bubble overcame the density of the cavity itself, and these things floated. And we didn't want them to float, we wanted them to sink. So we actually added about 40 nanometers of gold to the outside to make them dense enough to sink to the bottom of our chambers and things like that. And that worked out pretty well. And then by adding a hydrophobic layer to the outside of the cavity, we're able to basically trap a gas bubble because we make the shell so hydrophobic that water is not able to get inside when you take them from air and put them in water. And the thing that really excited us when we first tried to use these things is when you turn on the acoustic field, they immediately stand up. They stand up kind of to attention. And then from there, you can use the nickel layer and a strong magnet to propel them in different directions. And this is something that nobody had really seen before with these